latent vaporization is energy that you have to supply to convert the liquid into vapor. Okay, so this also is very important, and you can see that in some cases latent heat may be higher, boiling point may be lower. So in combination only we have to see whether the fuel is volatile or not. Okay, so specific heat is the property which is useful in supplying the sensible heat. So from the atmospheric temperature, so towards the boiling point you have to heat it. So that for that the important property is the specific heat, so that we have to take into account. Then latent heat has to be supplied to vaporize the fuel, liquid fuel to vapors, its vapors. So this specific heat here and latent vaporization and the boiling point, these three govern the volatility together. Okay, so that is very important to understand. So now these are the three important characteristics. So to classify, you have fire point and flash point, and to know about the volatility, understand something. So some numbers can be derived out of these three properties, and volatility can be defined. So fossil fuels, liquid fuel, the main fossil fuel is crude oil. So crude oil, you can see that it, so when you do an ultimate analysis of crude oil, ultimate analysis which is done to understand what are the elements constituting the fuel. So you can see that crude oil contains 80 to 85% of carbon, 10 to 15% of hydrogen, and traces of sulfur, oxygen, nitrogen atoms, and so on. So sulfur is present, please understand that. So that is what I am saying, that see, if you take a gaseous fuel, we can avoid these impurities. Now we can see that we cannot avoid impurities in the liquid fuel, and the solid fuels it will be more like you will see more impurities basically, like minerals itself will be there. Even in liquid fuels, minerals will be present. Okay. Now when the crude oil cannot be used at all for any practical applications, because it is very thick and black oil, very high viscosity and so on, it can be used and it can be even vaporized easily. So it has to be subjected to a process called fractional distillation, by which you get a lot of components like petrol, gasoline, kerosene, diesel, etc. So these are increasing molecular weights, densities. So now these are the components which we get, the liquid fuels from the crude oil by processing it using fractional distillation process, and these fuels can be used in automotive and aerospace applications. Even in industrial burners we use diesel based, so diesel oils, heavy diesel oils, etc. can be used. So see, for example, diesel, heavier than diesel cannot be directly used in the automotive application. So but in industrial applications we can use it. So we can actually preheat it or supply steam along with it, so that you can atomize it. Okay, so you have to, for atomization you have to bring down the viscosity. So that can be achieved by heating the liquid or adding steam to it and so on, and that is primarily done in several industries. Okay, and please understand that every component which is generated from crude oil is multi-component in nature. It is not a single liquid, it is a multiple liquids mixed together. So multi-component in nature. Okay, so that is another main point we have to understand. So when you analyze these fuels, we have to understand what are the constituents of this. So that the characterization should be done. But one fortunate thing is, when they burn, they don't display the multi-component nature. They burn as though they burn as a single component fuel. So that is the advantage of these three fuels, basically what we use in day-to-day applications. Alternative or man-made synthetic liquid fuels or alcohols. Then if you can use solid fuels to make liquid fuels. So liquefied solid fuels and vegetable oils. So vegetable seeds are produced, grown, and they can be converted into vegetable oils. Vegetable oils can be processed through a process called trans-esterification, where you will get biodiesels. So these are the ways. So normally you take solid fuels and convert them into this alternative liquid fuels. So solid fuels can be converted into gaseous fuels or liquid fuels. So if you take alcohols, ethanol, methanol, etc. are the examples. Methanol is produced from natural gas basically, or you can also use CO and H2, a synthetic gas, and from that you can produce methanol. Okay, so solid you can produce the synthetic gases, and from the synthetic gas you can produce methanol. Okay, that is another one route. Then ethanol can be produced from sugarcane bagasse. So sugarcane industries produce ethanol in large quantities. So, alcohols like methanol, ethanol, etc. can be produced from solid fuels or gaseous fuel, natural gas and so on. Then solid fuels also can be liquefied, like for example, if you take solid fuels, again bagasse is example, or some etc., you just gasify it, takes in gas, and Fischer-Tropsch type of process can give you liquid fuels. But the conversion efficiency etc. are under research. It's not actually the scaling up and conversion efficiency etc. are not thoroughly understood, but it is producible. So, liquid fuels are produced from solid fuels and from gases, like gasifying that. So, vegetable oils you can grow, like for example, there are edible and non-edible crops we can have. See, for example, sunflower, corn, etc., or jatropha, karanja. So, these vegetable seeds can produce vegetable oils, and you can use them to produce biodiesels. Okay. So, ethyl alcohol is obtained from sugarcane, bagasse and corn etc., and ethanol can be blended with gasoline and used directly in engines. Please understand that directly we cannot use biodiesel or ethanol in an engine, because engine is designed for using diesel or petrol and so on. So, directly using ethanol in engine, it may be possible, but we do not know the long term consequence of that. So, for example, what will happen in terms of corrosion and other things, we do not know. So, blending has worked very well. Blending ethanol, say 20%, 30% ethanol with petrol, and using that. So, that means that we are bringing down the usage of the fossil fuel to that extent. Okay. So, similarly, biodiesel can be blended with diesels and used. Okay. So, biodiesel, basically I am coming to that next. So, you can produce from vegetable seeds, rapeseed, sunflower seed, neem, jatropha, karanja etc. So, edible and non-edible these seeds, and you can extract oils from that. And when these oils are actually cannot be used directly because they are very viscous. To bring down the viscosity, what you do is you do trans-esterification with alcohols like methanol or ethanol. So, you get methyl esters. So, they are called biodiesels, and that can be used with diesel in engines. Okay. So, coming to the solid fuels, see, there are 4 important components in a solid fuel. First of all, solid fuel can be classified into 2 categories. One is called charring fuel and another is called non-charring fuel. When you take charring fuel, what happens is when you just heat it, okay, moisture goes out and volatiles goes out, and you get some carbonaceous material, some carbon plus some minerals. So, if when upon heating a solid fuel, if you get a carbonaceous material, then such a fuel is called charring fuel. Okay. On the other hand, if you take say plastics and wax etc., you just heat it, it will melt and it will vaporize and it will burn. So, there is no carbonaceous materials or minerals left as a residue. So, those fuels are called non-charring fuels. But mostly for industry and cooking applications, we use coal and wood. So, these are charring fuels. That means they leave the char as a residue upon heating up. So, generally what we have is there are 4 components present in the solid fuels, charring solid fuels: moisture, which is trapped water vapor, then gaseous substances which are called volatiles. So, when this wood is transformed to coal, lot of things are happening under the ground. So, moisture, gaseous fuels, everything is trapped inside, and based upon the quality of the solid fuel of say coal for example, if the fixed carbon content, the third content is fixed carbon, you will have carbonaceous material, and ash is the mineral component. So, these are the 4 main components which we get, but the rank of coal is mainly done with the fixed carbon content. If you have a coal with very high fixed carbon content, say 90% above, then we call it anthracite. So, that is the highest ranked coal. Okay. When the carbon content decreases, then we go towards wood. Okay. So, anthracite, bituminous etc., and we go, the wood has the least carbon content. So, in that case now you will get more volatiles. So, volatiles will be higher, maybe moisture may be higher and so on. So, these are the four components which we get in a charring solid fuel: moisture, gaseous substances called volatiles, fixed carbon and ash. So, the fixed carbon and ash together is called char. Okay. So, you can see the heterogeneity or heterogeneous nature of the solid fuel. It has liquid like moisture, then it has gases, and it has minerals which are inert and so porous substances, and also it has carbon, it's graphite. So, this is very important. So, now we can see that it is not very easy, it is a complex fuel, it is not very easy to burn this. So, burning a wood also we need lot of things, lot of analysis you have to use and design your wood stove properly and so on. It is not so efficient to burn it easily. So, we have to do lot of research, and so the easiest way is to gasify this and produce gases, and use the gases to produce liquids and so on. So, that is what we are trying to see. But if you want to burn it, you have to really carefully burn it, and if there is any variation in the contents like these four contents, then we are going to get a different set of results. Okay. So, how to get these four contents: moisture, volatiles, fixed carbon and ash? So, you do what is called proximate analysis. This proximate analysis basically when you try to heat this solid fuel gradually, so some heating rate you can set and heat this in proximate analyzer. So, first we can use a inert gas like a nitrogen. So, nitrogen, hot nitrogen gas can be used to heat it slowly. So, what happens when the solid is heated to say a temperature of about 100 degrees, the moisture escapes, okay, 100 degrees plus moisture escapes, then it further continued heating. So, when the temperature reaches in between, so 350 degrees to about 500 degrees, slowly the trapped gases are going to come out of that and they will go out. So, now you know the original mass, and as these moisture and volatiles escape, you can continuously measure the mass. And you can see that there will be change in the mass loss curve. By tracking that, we will know what will be amount of, what is the percentage of moisture present, what is the percentage of volatile present and so on. Okay. Now, after that, see, when you just pass on nitrogen continuously, you will not see any change after the moisture and the volatiles leave the material. Now, you will see that the mass loss does not change at all, the mass loss curve becomes constant. So, now what you do? You have to shift to a oxidizing medium. So, now supply air or oxygen. When you do so, what happens is the fixed carbon starts burning. After it reaches a particular temperature, say 800 to 900 degrees centigrade, the fixed carbon starts to burn. Then you will see the mass loss again. Now, after a particular point, only ash will be left, and that will not burn at all. So, that will be inert. So, the heating will not have any effect. So, that you will see that will be the percentage of ash. So, by this analysis we can get all the weight percentages of all these components: moisture, volatiles, fixed carbon and ash. So, this is the proximate analysis. As I told you, solid fuel is ranked based upon the fixed carbon content. So, as I told you, this is the chart. Wood has 45 to 55% of fixed carbon. So, go down, anthracite is the highest rank coal, 92 to 98% of fixed carbon. Then semi anthracite. So, when you reduce the fixed carbon content, you go towards the wood. So, lignite, yeah, 62 to 72% of fixed carbon and so on. So, this is the typical. So, please understand that these are typical variations, and these fuels depend upon the region where they are available and so on. So, it is not say for example, lignite available in say for example, Tamil Nadu Neyveli is different from lignite available elsewhere. Okay, so that is the main thing. So, we have to understand the composition of the coal or any solid fuel before using it in any application. So, that is what the heterogeneity is about. So, very tough to really use it because of the complex nature. And also please see that you can also have for example, when you mine the coal at one place, you will get some property. If you just change your mines, then the property will change and that may affect the performance of the combustion. So, that is another important like a complex nature of these fuels. Okay. Now, there is another analysis which we normally do with the solid fuels, which is called ultimate analysis. This ultimate analysis basically will give you the percentages of the elements contained, like what we saw in the crude oil, how much C, H, N, S, O are present. Similarly, the same ultimate analysis can be done for coal or biomass, where you will get the percentage of elements such as C, H, N, S, O, etc. And please understand that when you do this, normally this carbon what you get is carbon which is present in the volatiles plus the carbon which is present in the fixed carbon. Okay. So, ultimate analysis will give the total carbon content, but by proximate analysis you will know what is the fixed carbon and what is the volatile. So, now what is the carbon content in the volatile can be separately determined by using the combination of ultimate and proximate analysis. Okay. Now, once you know the ultimate analysis, you can find the heating value of the solid material. For example, a formula called Dulong's formula can be used to find the heating value in megajoules per kg. So, heating value is calculated by using this. Okay. So, for example, carbon percentage, hydrogen percentage, etc. are known, then you substitute those in this to get the value in megajoules per kg. Okay. So, basically when you get this CH values, etc., this should be done in dry basis and ash free basis. For example, you know what is the ash content and moisture content. So, that you have to subtract and make the calculations in dry and ash free basis, and those values are substituted here to get the higher heating value of the substance solid material. So, or you can also use bomb calorimeter. So, this is the formula. Theoretically you can, this is a correlation which we got from literature, and we can use this basically. Okay. So, coal, the wood, etc. Basically are the biomasses which we have we use for several applications. Now, the vegetation, say rice husk, rice straw, sawdust, wheat straw, wheat husk, etc. They are all renewable solid fuels. See, now if we take India for example, we produce rice and wheat to very large amounts. So, abundantly we produce that. So, the rice husk, rice straw, etc. are also available. So, instead of just throwing it away, we can use it for producing liquid and gaseous fuels. We can also burn it in some furnaces, okay, some great burners, etc., and produce power straight away. But instead of that, we can also store this by converting this into liquid and gaseous fuels and store this. Maybe converting into liquid fuel will be easier for us to store this basically. So, these are the alternative solid fuels which can be used for several applications. Okay. What is the difference between coal and say sawdust or rice husk? The density. Okay, coal has a very big density. Say for example, very heavy, it's a very heavy material. So, density can be about say 1600 kilogram per meter cube, 2800 kilogram meter cube. So, using a denser fuel, okay, pulverize it and using it, that is different. When you have very light fuel, you cannot just use that as the same way as what you use as coal. So, normally what you use is you pelletize this and make pellets so that to increase the density, and you can use that as the feed for your burners. Okay. So, lot of applications are there. Directly you can burn this or gasify it to produce gases and liquefy that to produce liquid fuels and so on. Okay. Now, so far what we have seen is the fuels for industrial applications, domestic applications and so on. Now, some special fuels what we use for space applications is listed here. I am not going into detail, just telling about some fuels. Say for example, hydrazine N2H4 decomposes by itself exothermically at high temperature. So, when it is heated to about 600 degrees centigrade, it decomposes, and when it decomposes, it is an exothermic decomposition. Okay. So, that produces heat. Okay. The exotic catalysts made of iridium and molybdenum are used to decompose this. So, catalyst based decomposition can happen, and gases are produced, and these are called monopropellant, which are used in rockets, small rocket engines, monopropellants. Okay. Then for example, you say unsymmetrical dimethyl hydrazine then red fuming nitric acid. This combination can produce chemical reactions, and this is used in liquid rackets basically. So, similarly, in cryogenic liquid racket applications, you can use liquid hydrogen, then liquid oxygen as the fuel and oxidizer. So, these are the space applications, the fuels which are specially used for space applications. Okay. So, the oxidizers, as I told you, liquid oxygen is one of the things. So, we can also use instead of only liquid oxygen, you can also use nitric acid, then red fuming nitric acid, etc. Then this can be used for wherever the oxygen content is more, that those can be used as oxidizer in the space applications. Okay. So, similarly, solid propellant rockets use this polymers basically. So, polybutadiene with hydroxy or carboxy termination, these fuels, okay, complex polymers can be used for solid propellants basically. So, ammonium perchlorate can be used for oxidizer in those applications. Okay. So, these are the fuels which are used for special applications for space. For others, we can see, for example, for power plants, etc., we use different types of fuels, liquid fuels as well as solid fuels we use in power plants. For automotive applications, we predominantly use liquid fuels, and for industry heating purposes, etc., or domestic cooking, domestic and commercial cooking, we use gaseous fuels. Okay. So, this is the end of the first topic, fuels and their properties. So, we will continue with the second topic later. Okay. So, review of basic thermodynamics and especially for the gas, ideal gas and mixtures.